Edward Lee will talk about qualifying system F sub.
Hello,
Yes,
can you guys hear me now? Okay, sorry. So I'll be talking about joint work with my collaborators Yaoyu, Ondřej, James, Kavin, and Jonathan. Yaoyu's now at EPFL, Ondřej's my advisor at Waterloo, James was my lab mate, and he's now at Qualcomm, and Kavin's an undergrad that we had help out with this project, and Jonathan's a collaborator and friend at Tübingen. And these are their pictures, so you can see their faces. So what am I going to talk about today? So static type systems classify the values a program reduces to. So here's an example function, 2 lowercase. It takes in a string, and it returns a string. That's really well and good, and lets us prove useful properties about 2 lowercase that are good for making sure your program's correct. But how would we convey that 2 lowercase leaves in unchanged and doesn't blow up my ears? Well, there are 2 options you have here, and hopefully these won't take out your speaker system. You can view it as a property of 2 lowercase, which gives you down a whole line of work down coeffect systems, which are really cool, which we cited, which I think started from Patrick Sick in 2014, or as a property of n, the variable itself, which draws from a long line of work starting from Foster's 99 PLDI paper on type qualifiers. As you might have guessed, given the name of this talk is about option 2. So we can throw on a type qualifier on top of string, like const, to say that, hey, 2 lowercase takes in a string, but it takes in a const string, so it won't mutate its arguments. Type qualifiers have been used to model a whole bunch of extensions to existing type systems. The one we saw here was immutability, const. There's also exception safety, which most famously, I guess, comes up no except from modern C++. Nullability in various forms, like in non-null from C#. And there's a whole bunch of work that is done in the checker framework for modeling a whole bunch of extensions, like energy consumption, determinism, you name it. So why do we use type qualifiers? Well, they offer a pretty sound, a pretty mathematically principled, and lightweight mechanism to extend an existing type system. Qualifiers, as Foster pointed out, you can take them from, they have this nice lattice structure, so you can take your qualifiers from some lattice. For really simple qualifiers like const and non-const, they're just the top and bottom of a 2-point lattice, so that's really handy. You can adapt an existing type system with the lightweight subtyping that you want from type qualifiers by exploiting the order equipped from the qualifier lattice. 2 qualified types are in a subtyping relationship when the qualifiers are ordered properly in the lattice, and the types are in a subtyping relationship. And meets and joins from the lattice allow for some expressitivity. I hope I spelled that right. For example, if you compose 2 functions, like in the qualifier system that deals with exception safety and throwing, well, it throws if either of them or their join union throws. So what's today? Well, type qualifiers themselves are pretty well studied, but polymorphism over type qualifiers is a little less so. And why might you care? Well, let's go back to no except as a qualifier system. Here's int map. It's int map because I don't want variables right now. It takes a function f and a list L, and it applies f to each element in L and returns that list. When does int map throw an exception? Well, int map throws an exception possibly only when f throws. And you can't use subtyping to relate the contravariant qualifier of throwing on f to the covariant qualifier on int map. So you have to use a you have to use a variable here. So you add some qualifier variables. Fine, that's natural. But so okay, easy, sure. Or is it? Well, let's look at a more complicated example in compose. Here you've got 2 functions that operate on ints and return ints. And well, what is the result of int compose? When does that throw? Well, if we knew what the qualifiers Q and R, whether or not F or G throws, we could fill it in with their union, their lattice join, but they're variables now. So how can we fill them in? Well, ideally, we want to write down the lattice, like the expression Q join R, but that raises a whole bunch of questions, like how does this textual expression Q join R relate to either Q or R? Can we do this without losing the lattice structure that qualifiers give us, which gives us this nice subtyping property? And the answer is, well, yes, there luckily is. As people doing universal algebra would call it, there's a nice lattice that relates expressions on lattices as a lattice itself, and that's called the free lattice construction. So what's the talk outline going to be? Well, we'll give some definitions that are useful for us, hopefully for the free lattice, and we'll build a couple of systems to show you how you could use the structure. First, in the base system, System F sub q, not very creatively named, for modeling type qualifiers with polymorphism. And also, we're going to exploit F sub q and reuse it as a design recipe for some cases where qualifiers and polymorphism over them will prove useful, such as reference immutability and function coloring. And we'll see how we can re-examine some existing qualifiers systems out there with the structure. So here's a definition of a free lattice. It basically tells you, there's this complicated math definition, but it basically tells you that the free lattice orders lattice expressions by how they're ordered in every lattice. Now, that's not very useful, but it's also kind of a mathematician's, so it's kind of a mathematician's definition. It tells you what the object is, but doesn't really tell you how to use it. So what do we do from that? But there's this nice handy theorem that's kind of folklore, because it's been done a whole bunch of times, that gives a bunch of that defines the ordering relationship on the set of expressions, set of lattice expressions over a set of free variables x that tell you what exactly the free lattice is. And there's like a bunch of rules. They shouldn't look too surprising because they're kind of like what you'd expect for deduction rules for lattice, for order in a lattice would look like. And that's really handy because like this is almost exactly set up for natural deduction rules. So we can take these rules and write out really familiar subtyping or subqualification rules for computing when two things are subqualified by each other in the free lattice. So it's almost the same rules except with transitivity modified to allow for bounds on variables because we're working in a variant of System F sub, which has bounds on type variables. For orthogonality, we want bounds on qualifier variables as well too. So what have we seen so far? Well, we've seen how expressions on lattices can be encoded as a lattice themselves, and we can see how the lattice order on the free lattice can be expressed using type inference rules that are really familiar to us. So we can use this to build a base system for that you can reuse as a basis for other systems involving qualifiers and polymorphism, and I'll show you how to do so. They're also in the paper too. So we're going to take to get our base system with type qualifiers, we're going to take System F sub, because it has polymorphism and subtyping, and extend it to support qualifier polymorphism using the free lattice and qualifier and subtyping and counting for the qualifiers or subqualification. How we're going to do subqualifications, we're going to just use those handy subqualification rules, which encode the lattice rules of the free order. And polymorphism over qualifiers with bounded qualifier variables, same way as you have bounded polymorphism in F sub. And to equip our calculus with some base runtime semantics so you can actually prove meaningful soundness theorems, we're going to tag each value, we're going to tag our values, and we're going to construct them with the qualifier expression they should be qualified with, and we're going to add runtime constructs for checking like assert and upcasting qualifiers accordingly. So you can prove some standard theorems. Those are some standard theorems. What does that buy you? Well, using progress and preservation, you already get that type programs with type qualifiers won't get stuck. And with the additional runtime constraints for checking and upcasting qualifiers, we get meaningful safety guarantees on how qualifiers are used, which we can use to remix as a basis on the design recipe for some extensions. There are 3 in the paper. For brevity, we'll only do 2. So we're going to start talking about, I'll start by talking about reference immutability. Now, a reference immutability system is a type qualifier system that uses const, except this time const is transitive. When you read a variable, when you read a reference out of a const qualified reference, like a reference to a struct or something, you get back a const qualified reference regardless of, well, what it was before. So we can use the system to deal with polymorphism and reference immutability by, well, basically using the lattice join to adapt the qualifier on a value read from a cell or a record with a qualifier, whether or not be polymorphic or not, on the outside reference itself. And to give it some meaningful soundness properties, we'll just read the tag, the qualifier tag on the value, to check at runtime whether or not you can write to it. You get some standard theorems, progress and preservation, except this time with stores. What does this buy you? Well, it gives you that well-typed programs won't crash right into a const qualified reference cell. That's immutability safety for free. And with a little bit more work, you can show that qualifiers don't really affect reduction otherwise. So like you can erase the qualifiers and still get the same behavior, which is really nice. Another application which we examined, a case study, was function coloring. And function coloring shows up in many forms. Today, we're going to, like async or await, or throws and no except. Today, we're just going to talk about colors for simplicity. Two colors, red and blue. Red functions can call blue functions, but not vice versa. And red functions in this case can represent async or throws, and blue, no except or sync. As we observed earlier, when we talked about compose, we often want to take the join or the union of two colors when dealing with higher order functions. So this is a useful application. So we'll extend System F sub q to model this by modifying the operational semantics to check the colors before allowing a call to proceed, and the typing rules to propagate colors or qualifiers in an effect context. The details of this are all done in the paper because there's a lot of typing rules and we don't have that much time. But you get some standard theorems that tell you that, hey, progress and preservation all hold. And what does that buy you? You get that a red function is never called above a blue function during evaluation, just from progress and preservation, with how the typing and evaluation rules are set up with this nice general framework. So what about other qualifier systems? Well, so the work that we presented today was kind of came out of a bunch of discussions we had with some collaborators of Jonathan and I's at EPFL. Alex, I don't think he's in the room right now, but we were working on the system for tracking the variables captured or captured by a value for doing some sort of effect safety, for doing an effect safety system, which I think they presented as a Toplas presentation at POPL this year. And there's been some really related work that Sung Lin is going to talk about today on polymorphic reachability types, which is coming up soon, so stay for that talk. Now, and there's actually some other sort of related work that's kind of surprising that uses the same ideas as capture tracking, except with method names for tracking effects by using method names as a proxy for the effects they call, done by Gariano et al. In the 2019 Onwards paper. So what do they all share in common? Well, when we designed capture tracking, we had these sets of capture variables. We really couldn't figure them out, and we had these ad hoc formalisms for dealing with these sets that qualified our types, and their bounds and transitivity and whatnot. And so did Sung Lin, and so did Gariano. But if you think a little bit about it, sets are just lattices without intersection, and you can view sets with union, and all these calculi, since they don't have intersection, you can view their set expressions as just, lattice expressions on the singletons involving the singleton sets on the joins of all their variables or singletons. There's a lot more cool ideas that Sung Lin will present about freshness, which we won't get into. But for a lot of the stuff that we did, and that relates all of this, is that you can actually recast all of those rules, a lot of those rules, using this little handy bit of universal algebra and some subset of the sub-qualification rules I presented. Just since there's no intersection in those systems, just get rid of those rules. So what are the takeaways? Well, hopefully you can see how you can use free lattices to nicely encode polymorphism for qualifiers. Hopefully, our base calculi gives you an inspiration to design your own calculi if you need to use type qualifiers with polymorphism. We've got a bunch of case studies in the paper which might help you there. And yeah, hopefully we've re-examined some recent qualifier systems to see how they fit in this framework. So yeah, thanks for your time. Are there any questions?
Okay. If there are any questions, then
Thanks for the talk. This is really cool. I would love to see if this can encode tables, type system for tables. Like TypeScript has a key of operator, which says I have a type coming in. I don't know what it is, but it's going to be a key for this object, which is my other argument. And this works because key of makes sense for everything in JavaScript because everything is an object.
Right, right.
I don't want to live in that world.
You don't want to live in that world. So I think there's some, I think you might like yes and no. Well, I think possibly. I think there's some there's some closely related work that Magnus Madsen's doing on using things that are really related to lattices, Boolean algebras for encoding records, extensible records that we're actually trying to hopefully smush together with our theory of subtyping with their theory of Boolean algebras. So come back in a couple of months and hopefully we have an answer for you. But we're trying to write that up right now. So we're trying to work out the details. Hopefully it'll be figured out in 2 weeks, but fingers crossed.
Hi, cool talk. So this reminds me a lot of universal polymorphism independent type theory, and especially like with subtyping cumulativity. Can you speak to more about the similarities and what ideas were sort of borrowed from that, and what can be maybe brought back? That sort of
capture tracking came out of a capture tracking capture tracking, I guess, is inherently, which this work was kind of inspired by, came out of a fairly dependently typed system because it has term variables in type position, these qualifier sets and these capture sets, right? We've tried to avoid like dealing with dependent types as a concern that's orthogonal to us. We did give an encoding of capture tracking in the paper that gives a lightweight form of dependent type theory, but really lightweight in the sense that you have to annotate, you have to effectively annotate at your call sites what should be substituted in capture position to avoid a lot of the pitfalls that we had designing capture tracking with monadic no more form or variants that really caused a few landmines. So yes, maybe, hopefully is the answer. Hopefully that answers your question.
You had a lot of nice meta-mathematical properties, which is great. But one thing I didn't get a good intuition for is, did it actually work on, did you try it on a bunch of programs? I mean, it looks very promising, but I just wonder if there's some incompletenesses. I mean, that's really more.
Well, I guess like the universal algebra gives you the fact that like this does encode the right thing because like everything you want, anything that you abstractly want, you should be able to prove in the free lattice setting. Have we tried this on programs? No, this is strictly a theoretical paper. We are working on an implementation on an extension with the Flix people, but like I said, I'll hopefully get back to you soon about that.
Okay. Thank you, Edward. Great talk.